It's my great pleasure to introduce Professor Jonathan Tan. Professor Jonathan Tan received his PhD in astronomy from the University of California at Berkeley. He then moved to Princeton as a Lyman Spitzer postdoctoral scholar in theoretical astrophysics. And after that, he moved to Europe, where he spent 3 years at the ETH in Zurich as a Zwicky postdoctoral fellow. After which he returned to the United States as assistant professor and later on as associate professor at the University of Florida. In 2017, Professor Tan moved back to Europe as a professor at Chalmers University in Sweden. He's also a research professor at the University of Virginia, so he split his time between Europe and United States. Today, he will talk about the massive star, and the title of his talk is Open Question in Massive Star and Cluster Formation. So without further introduction, I now turn the control to Professor Tan.
And I'm going to tell you at least my view on massive star and star cluster formation and where things are at the moment. So it's not quite a review talk. I'll tell you some of the stuff we're doing in our group, and there's lots of people working with us right now. We have a big summer student program actually going on right now. So many of the students are working on aspects related to massive star and cluster formation. Okay, so massive stars and star clusters have been important, we think, throughout the universe, from the very first objects, which may well have been massive stars or even supermassive stars, to basically everything we're seeing in galaxies. They're lighting up galaxies, providing the heavy elements, setting the environments around supermassive black holes and galactic centers, and star clusters, where most stars and maybe planetary systems are formed, are in close proximity to massive stars. So for many reasons, we're interested to understand how they come about. So star formation in general then has many open questions, I would say. We don't really know why particular regions of giant molecular clouds form star clusters. So are they self-gravitating clumps that decay, lose their turbulent support or magnetic support and become unstable? Or is it triggered by some external mechanism? Then the initial conditions at the start of star cluster formation or at the start of star formation, how close is that gas structure to equilibrium, particularly virial equilibrium? As we'll mention now, there's still a debate going on about the basic accretion mechanism. Do we gather material in self-gravitating cores first, or is it a more competitive process? The overall timescale of individual star formation and star cluster formation is debated. The end result, the initial mass function, multiplicity properties, this is what any theory of star formation should eventually aim to predict. And many of these theories, that's what's guiding them, in fact. And so the initial mass function, of course, peaks around just below solar mass and then has this power law behavior and probably a truncation at around 150 solar masses or so, depending where we are. Okay, so ngVLA, right? I don't know much about it. I was on a long plane ride a few days ago, so I was printing out all the white papers from 2020 decadal survey, hoping to get some sleep actually reading, but the science was so interesting that it kept me awake all through the flight. So here we have the frequency range from about 1 gigahertz to 116, so we can get CO lines. Basically, we can probe atomic gas, molecular gas, ionized gas, measure temperatures, dense gas traces, plus of course the continuum, synchrotron free dust thermal emission and spin dust emission. But one of the key things on this diagram is fairly amazing to me. Look at the angular resolution here. So if this long baseline array is in place, we are reaching 0.1 milliarc second, which seems to be better than anyone else. So that is maybe something we'll come back to. Okay, for massive star formation theories then, as I've mentioned, the basic formation mechanism is still under debate. So core accretion is extending work from developed for low mass star formation. Many groups have done this over the years. With Chris McKee, we worked on what we call a turbulent core model. The basic idea is we have a self-gravitating clump. There's some internal pressure here set by the weight of the gas. This is the mass per unit area. Typical values are actually about 1 gram per centimeter squared in the galaxy for these massive star-forming clumps. Thermal pressure alone cannot support such a structure, so it's some combination of turbulence and magnetic fields. So fragmentation regulated by turbulence and magnetic fields, we think, produces a population of cores, pre-stellar cores, which then have their initial conditions set by this environmental pressure. That's the basic idea. And so in a higher density region, your starting condition is denser and will then collapse with a higher accretion rate. So we have the core accretion cartoon in here, collapsing with an accretion rate basically set by the local free fall time. Now, alternatively, mostly derived from work in numerical simulations, we have so-called competitive accretion. So here you see sometimes, only rarely, we would have massive cores collecting their material and then collapsing. Here we have really collapsed to low mass protostars first, and then the massive ones later gather the material, and actually on fairly long time scales. So clump fed or turbulence fed in some of the later models here. But it takes more time to bring in that material. Actually, accretion rates are significantly lower. Now in the closest region, Orion, something funny is going on here. It seems like a fairly explosive outflow, which has been linked to potential merger of protostars. So in fact, all three mechanisms are being actively discussed still, even in the nearest massive protostar. So low mass core accretion, just to bring everyone up to the same page here. This is a cartoon you may well have seen before. Self-gravity rounds the cores, it collapses some angular momentum, probably regulated by magnetic fields, also driving outflows which clear away the material. And it's amazing now that we have such beautiful data from ALMA, which, you know, look at the lovely symmetry in some of these cores here, showing that maybe the model is not so crazy after all, at least for low mass star formation. Now in high mass then, this is the cartoon again. So we, in a time sequence, we would have a massive pre-stellar core, and then later, you know, the protostar is growing in mass, it crosses some threshold, arbitrarily 8 solar mass here, when we might say it's a massive protostar. So let's focus first on the pre-stellar cores. Are there massive pre-stellar cores? Do they even exist? What's their dynamical state? And then perhaps something about the core mass function. And then later we'll come back to the protostars. So this turbulent core model is assuming virial equilibrium of this core, so it makes predictions for the, you know, what's the velocity dispersion and so on, and equicondition magnetic field strength. So a 60 solar mass core in a clump of 1 gram per cc would have 0.06 parsec radius, about 12,000 AU, but it depends on the environment. If you go to a denser region, it'd be smaller and denser. And the velocity dispersion is about 1 kilometer a second, so it's turbulent. And the local volume density of the surface is already 1 million hydrogen nuclei per cubic centimeter. Now, simulations are progressing. Many groups, including our own, are trying to simulate the initial conditions. So here's an example of actually cloud collision simulation, which produce a whole bunch of dense gas structures and cores. There's hundreds of cores in here. I personally think that the combination of magnetic fields and turbulence, which are regulating things. So we have examples which are fairly strongly magnetized, so starting with 10 microgauss, we're amplifying that up. And we have this characteristic filaments and chains of cores, which I think are quite realistic. Then with Chi-Young Su, we actually put a couple full astrochemistry into this. And so in particular, in cold dense conditions, CO freezes out and deuterated species like N2D+ become abundant. So this is actually one of our main diagnostic traces for the cold dense conditions of pre-stellar cores. So typically we're going to ALMA, we're looking for dark clouds, one, we call it cloud masses, it's always in the galaxy, so within about a 10 parsec region here. We've looked at ALMA since the very early days of ALMA, going after this ND+ against our mid-infrared extinction maps, and trying to find examples of massive cores and characterize. Okay, so we're looking at these infrared dark clouds, trying to find massive pre-stellar cores from N2D+, a deuterated species of trace cold dense gas. And as I was saying, you know, we're characterizing them dynamically. One problem we have is measuring the temperature in the regions. The temperature is needed for both the astrochemical calculations, but also just the mass estimate from the dust continuum if we're using thermal emission. And we've been relying on ammonia observations from the VLA, few arc-second resolution. So one area, assume the ngVLA will be able to improve on much better is such temperature maps. Because with ALMA, of course, we're pushing to resolutions easily around 0.1 arc seconds to look for these cores, and they're often in quite crowded environments. This is, we think, one of our best candidates in that cloud, and nearby are some protostars forming. Some of these we think could become massive protostars as well. And this is a map of the whole, a large part of that infrared dark cloud. That was that region I was showing you. So the green is the millimeter continuum, and CO, red and blue shifted outflows are here. So one sees we can really probe cluster formation, massive cluster formation. But in general, when we're looking for the mass function of these cores, estimated by millimeter continuum, doing core mass function work, we're typically having to assume something about the temperature. It's not really measured on these scales. And so again, ngVLA can really help us there with perhaps ammonia measurements. Okay, let's go to the later stages. So the core accretion model makes predictions of the accretion rate, which sets the infill envelope, the disk structure, the protostellar structure, the outflows, and then we may begin to ionize these outflows. Now simulations, these are from a number of different groups here. You may worry, is that cartoon relevant? So if you have a weak magnetic field, you do have a lot of fragmentation. If you have more like milligauss fields here, then very limited, if basically no fragmentation. So as long as the field is relatively strong here, at least in some cases, we will form massive individual sources, or maybe with disk fragmentation. So we're going to work with that assumption in this cartoon here, just scaling it up to high mass cases. And we basically have just a few parameters. So we have the environment of the clump, we have a mass of the initial pre-stellar core, and then this is our evolutionary variable m star, so how much mass is gathered from the core into the star here. Then, of course, when you're looking at a real system, you have a viewing angle and maybe some foreground extinction. So our modeling includes protostellar evolution at the center here. We have an alpha disk model, we have an Ulrich infall solution, we have a disk wind, the Blanford pane, the self-similar disk wind. So all of these elements are in the model. We couple it to regular transfer for continuum, and we can make images and spectral energy distributions and basically fit these kinds of models to data. So that's what's done in this latest release here. And then try and constrain the input parameters. So sometimes not very well, sometimes better, but there's obviously degeneracies here. Now let's just have a zoom into one of these things. This is our 60 solar mass core, one in a typical environment at the stage of 8 solar masses. I put it at 2 kiloparsecs. Here is it's 10 arc, this is 20,000 AU, so 10 arc seconds across. This would be my initial core. It's opened and outflow at this point, which is this kind of angle. We have motions here. The outflow speeds are fast, could be close to 1,000 kilometers per second. So that's 0.1 arc seconds per year. I mean, I guess VLA can already see that. And then infall scale is more like 10 kilometers a second for the same arrow. So we'll see in here. As I mentioned, density is 10 to the 6 on the surface rising, and then the temperatures due to the heating here is fairly warm, of course, in the outflow and in the core as well. Now, if we zoom into 1,000 AU scale, so now the inner half arc second, this is what the cartoon looks like. So we now can see the infall motions, more than 10 kilometers a second here. The disk is down here, so it's what is it here, roughly 50 AU in size. And but that disk size is really just set arbitrarily, I would say. We've assumed 2% rotational energy. And also we don't have magnetic fields regulating this infall, so these speeds may not be quite as high as here. Now let's zoom into the inner 100 AU, so the inner 0.05 arc seconds. And now you can see it. So this 20 kilometer a second arrows here would be 4 AU per year, about 2 milliarc seconds per year, this distance. This can be seen by VLA, and if there's a binary here orbiting around at about 18 AU, you have this kind of speed. So that's one thing ngVLA can, with its resolution, can probe in here and try and look for these things. So with these models, it's an evolutionary sequence. So we have a history of the density and the temperature. So we can couple these astrochemical models. We worry about where's our formaldehyde ice line or methanol ice line. All these ice lines are in the core envelope here. And these are useful diagnostics, we think. But in the disks themselves, these conditions are kind of amazing, at least to me. We're mid-plane densities here, 10 to the 15. Going out, it depends how big the disk is, of course, but down to maybe 10 to the 10 if the disk is 100 AU in size. We have dust destruction, depends on the mass, but a few AU, maybe in the later stages, tens of AU. And these are very interesting conditions. Now, as you may know, there are a lot of super Earths out there, and we and others are very interested in actually in situ planet formation models where they actually form in their protoplanetary disks around solar mass stars at distances of order 0.1 AU. And these have conditions exactly like this, around 1,000 Kelvin, where dust is being destroyed. So when we make our models of protoplanetary disks around one solar mass stars, we have actually conditions that are not so different here. It's just maybe these will be easy to resolve, and ngVLA can really help us probe the chemistry in these kinds of conditions, which will be useful for planet formation work. If you want to read more about what's going on in these hot disks, I just refer you to Kei Tanaka and Chen Zhang's review here. Lots of interesting chemistry in these hot disks. Now, our protostellar evolution models predict an ionizing flux, so we can do little H2 regions in the outflows. That's what Kei Tanaka worked on in Florida. And we've been making predictions then of the photoionized contribution to the SED. So we have the thermal component we've already mentioned, and now the free component due to photoionization. Right now we're working on shock ionization in the simulations we run with these outflows to make a unified radio SED here. Okay, so let's go to some observations. I mean, many groups do it. In our own group, this is where we focus at the moment. So we go to SOFIA forecast. We look in the mid-far infrared. We're trying to get the full SED, thermal SED, to constrain the protostellar source. This is Cepheid says as an example. We got asymmetries here due to near facing, it's brighter compared to the far facing. And this is interesting because this is telling us the degree of asymmetry at quite long wavelengths tells us a lot of dense gas right around here. And this is the core. So is there a massive core around a massive protostar is one of the main differences between competitive accretion and core accretion. And this really constrains that core by its extinction. So we've observed about 40 of these objects and fit their SEDs. And this is one result in terms of the parameter space. We don't have any current protostars greater than 25 solar masses in environments where it's quite low surface density, whereas we're about 7 or 8 or 9 in higher density environments. This is mainly how we use thesis work. Now, our favorite interpretation for this is not actually the Krumholtz and McKee 1 gram per cc threshold that they published in Nature due to low mass protostellar heating. It's actually due to internal feedback. In denser cores, it's actually, you can form higher efficiency star formation. Whereas in lower density cores, internal feedback is more disruptive. So it's much harder to build up a more massive source. That can explain this distribution better than the other mechanism. So then to some of these sources, we go to ALMA. I mean, some of these are famous sources, of course. Here's a nice example of a fairly ordered bipolar outflow. We've got a method of formaldehyde ice line here, which is nice, around 3,000 AU. So it's a kind of very nice example, but it's not alone. There are many examples of pretty ordered, massive star formation out there. This is from Timenez and Yeri's work. Here's one, fairly massive, could be as much as 50 solar masses. We've wheeled out the VLA as well. And, you know, so we can do spectral index maps as potentially a synchrotron jet here. So it's an accreting system and still maybe, you know, 50 solar mass protostar. So again, ngVLA, of course, will really help us make beautiful spectral index maps here to probe their structure. Now we can go beyond SED fitting, so we can do profiles of intensity along the outflow axis. That's how we're starting. And with the Yaolang Yang, we're fitting the intensity profile, say in Cepheid A here. It's asymmetric, the blue side to the red side, and that's part of the modeling as well, so we can better constrain and break degeneracies in our SED model fitting. Now the same system recently published by a different group here looked at the radio jet, and they're also using that spatial information in the radio jet to constrain aspects of, you know, how collimated it is, or the recollimation zone in the outflow. So this is the level of which core accretion models are being tested now. We've got a binary here that we think formed by disk fragmentation right in here. This is long baseline ALMA, and we can measure its orbital properties through the H30 alpha recombination line. So we have examples of fairly ordered binary formation, I would say, with infill streams. Remember, core accretion has a turbulent core, so it's not a completely spherical object. It has structure in it, and this can still be understood in the context of core accretion models. However, what cannot are things like this from John Bally and Adam Ginsberg, and this is this famous explosive outflow in Orion, probably due to some close interaction or even a merger. We see from radio motions fast motions of some of the protostars and young stellar objects. In the last few slides here, let me just turn to cluster formation. The question I'm interested in is whether it's a slow process taking many dynamical times or free fall times, or whether it's fast. It's essentially competitive accretion. The first models were all fast cluster formation models, whereas in fact, core accretion, as we mentioned, sort of requires quasi-equilibrium boundary conditions on our cores. So we sort of want a clump to be able to establish pressure equilibrium. Now, that's not to say that there could be large-scale convergent flows or cloud collisions that actually help gather material, gather a lot of material into a dense clump quickly. But then once it comes together, perhaps internal feedback, outflow feedback can maintain turbulence and regulate this process and let it sort of stew and slowly cook its stars. That's the picture I have in mind, but it's debated. So this is, as I showed you before, the kind of structures we get from such collision simulations. Now with Juan-Farias, we're coupling these kinds of simulations or models of turbulence to orbital dynamics. And so we can look to see how stars are expanding as the gas is removed or maybe still contracting. And we can go to real clusters, so like the infrared dark cloud I showed before, we can characterize the protostellar populations. This is from Herschel 70-micron sources. We can fit their SEDs, we can estimate their masses from the SED models, we can look for evidence of mass segregation. This was Emily Moses' undergraduate project in Florida. We didn't find evidence, for example, for primordial mass segregation. Massive stars are sort of all over the place here, whereas some star formation models might say that massive stars have to be in the center. Now, ngVLA, it can measure motions. So internal motions here should be of order 5 kilometers a second plane of sky. So that's 0.2 milliarcseconds per year. So that's, you know, let ngVLA monitor such things for 5 to 10 years and measure their dynamics. Okay, so here are my conclusions. I tried to give you a little overview of massive star formation, obviously focused on core accretion more. That's what we're working on, but it's, you know, we have a core, massive cores, they know about their clump environment, that sets their properties. They don't look round, you know, that they have turbulence. We need to study their properties through astrochemistry and typically N2D+, the pre-stellar cores. This is a cartoon really involving semi-analytic models of physics of infall and accretion disks and outflows. We try and test them in simulations where we can. We're looking for massive pre-stellar cores, as I mentioned, especially with N2D+. So I guess ngVLA can also help us here. The continuum, these things are very cold, so it's typically, we don't see them very well in the Alma millimeter continuum, but maybe if we go to 7 millimeters, it's better. And we want high resolution temperature maps as well, also for pre-stellar core mass functions. For the massive protostars, lots of stuff happening. You know, for ngVLA in particular, the hot cores and disks, looking for multiples and measuring the dynamics, and then getting your outflows. You can really test details of the models, you know, how are outflows launched, where are the disks fragmenting, is it core fragmentation? Then for star cluster formation, I just mentioned one thing. I'm sure there are many other science cases, but in particular, I think only ngVLA can do this with embedded YSO and protostar orbital motions, so which would be great to test theories of star cluster formation. So thank you for your attention.
Thank you very much, Jonathan. Very nice talk and very interesting aspect. And I think, you know, you already went through some of the new things that the ngVLA could provide thanks to greater angular resolution and sensitivity. I would like to ask you a question. You know, you have talked about observing molecular line emission from this high mass core and continuum. What do you think will be the most important aspect that, you know, this new high angular resolution observation that the ngVLA will be able to provide my lead to? Meaning, you know, would you prefer to have a sensitive observation at 3 millimeter in molecular line emission? Do you think that, you know, having super high resolution at maybe 7 millimeter in continuum will change the picture or help pushing the theory forward?
Well, I think
they're all very good.
So let's see here. I mean, these, I've shown some examples of cores. We begin to resolve them. There are not many candidates for high mass pre-stellar cores. I think these are critical objects to go after because they really distinguish between the different models. You know, is the mass function being established in the gas phase, in the gas-only phase, or is it driven by the cluster environment where the protostars are already there? That is critical to go after. So
maybe you can remind us, so what are the main, I'm sure you kind of mentioned that, I'm not sure you said that directly, but what are the main mass tracer that people use currently to estimate the mass of massive cores?
Right, so exactly in this region here, in the background is a mid-infrared extinction map. You know, so that saturates around 0.5 gram per cc with Spitzer. You know, JWST will be better resolution, but will still saturate about 1 gram per cc. It just becomes too optically thick. Then you can go to the millimeter continuum emission, but we don't know the temperature very well. I mean, it could be as cold as 6 or 7 Kelvin. Those kinds of temperatures are seen in low mass pre-stellar cores, L1544, for example, in the Crapsey et al. Work. So, you know, if we don't know the temperature very accurately, we can't get the mass that accurately. So it's probably factors of 2 uncertainty, I would say, from the millimeter continuum. There's the dust grain properties as well. Probably the best way to get it is a dynamical mass, but again, the magnetic fields could be providing partial support. So those are the main ways. So, you know, the millimeter continuum here would really help, I think. But you know, the ammonia, or it's probing somewhat lower density environments around here would also be useful, very useful.
Okay, we have a question. And the question is, the ngVLA will hopefully be useful for studying forming high mass binaries. Have you included in any model which line are most likely to be detectable at, say, less than 10 AU scales, perhaps recombination line or salt lines?
Right, well, of course, Adam's work detecting sodium chloride in Orion is groundbreaking, and there are now a few systems where it's seen. So yes, these hot to disk species were probably connected to dust destruction. The beginning stages of dust destruction, I think, will be very important. So there are transitions, as I understand, in the bands that ngVLA can look at, and along the wavelengths is great. You can probe deeper in. Optical depth is less of a problem, or it probably still is optically thick at some point. So yeah, I think those would be very good. Just the continuum emission from the protostar is just to find the things is great. I mean, often when we start with our SOMA protostars, we're not quite sure where is the protostar, you know, so we're always going to the VLA and trying to find the radial continuum source, where exactly is the thing. And so if there are multiples in there, we should be quite sensitive, I hope. But as you may have seen in this disk here, I mean, the disk is quite thick, so you know, we have not yet put in binaries in this disk and try to understand how observable they are, but that sounds like a good project, actually. Maybe we should do that next.
And how optically thick will this disk be at, say, you know, 7 millimeter, 1 centimeter? Do you have an idea? Are they?
Well, let's see. Depends where we are. We'll give you an answer later if you're, but it's, you know, we've got surface densities of hundreds of grams, thousands of grams per cc. And so I think even at 7 millimeters, well, then of course in the inner we've got a lot of ionized species as well, so the capacity can go up. So there'll be regions that are optically thick even at 7 millimeters, for sure.
Yeah. So new, very interesting SOFIA magnetic field workshop is going on. Now, very interesting SOFIA magnetic field workshop is going on. People talk about very interesting polarization observation. Can you tell us interesting prediction from your simulation regarding the dust distribution and properties that the ngVLA will observe with high resolution?
Right, well, magnetic fields, I think, are making a return. They've been out in the wilderness for 20 years or so, but it was known they were there. And I personally think magnetic fields are crucial. So we need a way to stop these massive pre-stellar cores from fragmenting. And I think, to be honest, it has to be magnetically regulated. We're seeing these objects that are cold, So they're not heated much. It's not extra thermal pressure stopping them fragmenting. If anything's doing it, it's magnetic fields. It's difficult to get in the pre-stellar core phase because they're so faint in the continuum with ALMA. You know, I put in a bunch of ALMA proposals to go after band 6 polarization on pre-stellar cores, and been proved even, but it's never observed. Henrik Beuther's got one and found inferred milligauss fields. That's the kind of equipotential field we have, exactly about a milligauss field here for a pre-stellar core phase. I'm not an expert on ngVLA, but will it do polarization, continuum polarization? That would be, if it can, that would be great. So I encourage that.
So your prediction for magnetic field would be, in terms of polarization, we should see, as is predicted for low mass study, the magnetic field is kind of perpendicular to the or parallel to the outflows, roughly speaking. Is that what you would guess?
At later stages, I mean, Qiju Zhang's work and others that have seen a number of things. That's being seen by ALMA. At that point, they become much brighter millimeter continuum sources. So that's happening already with ALMA. You know, you worry about grain alignment, and you know, there's lots of going on in these environments here, but I think there's certainly a number of interesting cases where we see relatively ordered polarization vectors around the massive protostars. That's already quite a number of examples. It's more at this early stage, I would say, where things are less clear. One big question, yeah. We don't know the dynamical history of these cores. I mean, did these cores form very quickly? So they're just one free full time old, or have they taken a long time to sort of settle and gather? That's also important. And again, if it's magnetically regulated, that's probably how they would be slowed down. So yes, getting a good millimeter continuum polarization around these quite faint structures. Yeah, maybe ALMA can do something here, but it's may need something better.
I guess that, so ALMA has showed that polarization can be very messy if you are in optically thick or thickish region in continuum, because then you have to deal with set scattering. So I guess that eventually, if you zoom in too much, you might encounter the same issue where polarization might be driven not by magnetic field and grain alignment, but set scattering perhaps.
Right, but at the pre-stellar core stage, I think that's not going to be an issue. So certainly at the later stages.
Okay, so we have let's stay on the large scale, and then we're going to move a bit more toward what's going on very close to the protostar. There is a question of clamps about 1 parsec in size, 10 to the 3 solar masses seems to fragment early, as we see evolution of core mass fraction relative to the clamp mass. This also means core mass function evolves, and the fragmented core do not seem to have preferred scatter as observed in 2D. Some show filamentary distribution, some not. Could you please comment more on how do you picture a clamp fragmentation process in terms of high mass star formation theories?
Right, let's see what I can say about that. Well, empirically, people are measuring core masses, core populations in these structures, and measuring core mass fractions, and we've done it in such clouds, for example. We've just done a recent study in Vela, for example, which is we chose to be a fairly strongly magnetized region, and our core mass fraction as a percentage of the total mass was actually very low, 10 times lower than say in more evolved protoclusters. So certainly it evolves. I've seen values then from less than 1% in that strongly magnetized region in Vela C. That's a Cheng et al. 2021 paper. To values perhaps over 10%, even or more in say the G286 protocluster. So that's could be a nice evolutionary indicator of cluster formation. So basically looking at the PDF, how much mass is it different densities, and then one could probably higher order statistics how the mass is distributed. I think it's still open whether massive stars form early or late, or at the same time. I should have put my last thing here. I've got a whole bunch of questions here because when I should have said many of these things are still open, but so many groups would question this completely and say it's really competitive accretion. Competitive accretion would of course predict that the high mass stars form late. They take quite a long time. In these latest models, to form 20 solar mass protostar takes a few million years. And so at early stages, you really wouldn't have those protostars present. They don't have massive cores full stop. So massive prestellar cores and maybe not even that massive protostellar envelopes. We really need to go to those competitive accretion simulations and get their predictions for the millimeter luminosity functions, and then we can do some comparisons. And I guess those groups are doing such things. This fragmentation, I personally think, is regulated. We need non-ideal MHD processes because we do need to lose a lot of magnetic flux. We need to cross this boundary of magnetic criticality, and that requires ambipolar diffusion or some kind of reconnection processes. That's not modeled generally very well in many of the simulations at the moment. It's something that we're trying to do. So from our side, we don't have detailed predictions yet with that included, but we're working on it. We are measuring core mass functions now in some of the cloud collision simulations in ideal MHD, and we're able to start making comparisons. But the prestellar core mass functions are very hard to measure. Typically with ALMA, when we're looking at these things, we're measuring already protostars. You can see in here, these little green dots, most of them have outflows. So we don't quite know what the evolutionary stage is, what the temperatures are on those scales. So the masses are pretty uncertain here. So core mass function really is a misnomer. It's really core millimeter luminosity functions at the moment is what is being done. And then there's individual protostellar evolutionary uncertainties in each, folded into each estimate. So I'm not sure I answered your question. I'm not sure I remember your question, but it's a complicated business to try and couple all these things. And when we do have evolutionary sequences, then we need probably many large samples, so we can sample over different evolutionary stages.
Okay, thank you very much. Let's go to the last topic, and then we'll let you go. There's a question about planet formation around this massive star. And the question is, can you elaborate on how the initial condition for planet formation, for example, dust or disk masses, radial extent of disks, may differ between disk around massive star and solar mass star? And if I could add something to that, because that was also one of my questions, you mentioned a few times that your disks are very massive, hundreds of grams per centimeter square. Can you comment a little bit on whether they are gravitationally stable or unstable, and how it's gonna affect, the formation of planets? How you think it's gonna affect formation of planets?
Right. So, well, the disks, I think even around low mass stars, there's a lot of uncertainty in how the disks emerge due to magnetic braking. And again, we need non-ideal MHD, and we worry where the charge is it on the small dust grains, are the small dust grains frozen out? So that is a challenging topic, even when looking at nearby low mass systems. If magnetic fields are important in preventing fragmentation, so if I want a strongly magnetized region, then it's going to have even stronger magnetic braking. So, that's one aspect, and maybe relatively speaking, the disks may end up being relatively smaller compared, because there's more magnetic braking. I don't know really. We have to try and follow that non-ideal MHD with astrochemistry with strong magnetic field in the collapse. Now, observationally, there are disks now seen. They're even measuring tumor AQ parameters in these disks with ALMA. So Henrik Boyth's group has been doing this, for example, and they've been seeing tumor AQ values of order unity. That's not so surprising. But once a disk builds up enough mass, starts to become moderately unstable, then it's able to transfer angular momentum much more efficiently. So in some sense, you might expect them to regulate at tumor AQ of order unity. Now, as the disk grows in size, it's easier to fragment at the outer scale. So maybe coming later on, bringing in higher angular momentum material, the disk is growing in size. Maybe at some point, it just reaches a point where it can then start fragmenting. Maybe that's you know, maybe that's this evolutionary sequence to lead to this fragmentation. But that's probably going to form fairly massive objects and stars rather than planets. So coming back to your question, I'm not sure if I'd really say any planets form around these massive stars. So yeah.
Well, there is, you know, if I'm not wrong, the first planet discovered was around the pulsar, right? So, you know, there is evidence that there are planets around massive stars.
Right. I don't ask me to explain how they form.
No, but you know, yeah, it would be interesting now to, you know, because I think the question was, would you, you know, we don't know how planets form around the Loma star. You know, the general idea is by core accretion. I wonder whether perhaps around massive star, maybe gravitational stability might be a more likely formation pathway, or maybe probably
right. But I think that will lead to stellar mass objects.
Stellar mass object. So it's more binaries.
I think that's my expectation. And then once you have something formed, it's because it's further out in the disk, it's going to accrete more material. I mean, this tends to drive the mass ratio towards unity to form more equal mass sources. But even the starting mass, I think, would be fairly massive in these disks. We can work it out. I think Caitlin Cratter's already worked it out, so I think that sort of stellar mass objects in some of these disks.
Okay, very good.